Hey, thank you a lot for the introduction. So again, my name is Lou, and today I will talk about compute shaders and how you can use them in your engine efficiently. So first I will start and talk about what are compute shaders actually and what makes them different from other shaders. Then I will go into detail how shaders get executed on the GPU, how does it look like on the hardware, how is the work distributed along the different components of the hardware. And then we go one level lower into the programming. We look how can we code our shaders that they get efficiently executed on the GPU. And I will wrap it up with an example. It's downsampling is quite an easy example, and along this one, I will explain how we can use the concept I just talked before about for compute shaders. So let's start. So what are compute shaders and what makes them different from other shader stages? Kind of understand this, a short recap on what GPUs were originally designed for. So they were designed to do graphic stuff, right? So we have a bunch of meshes, which are represented by vertices. They get insert into the GPU, and the GPU is doing some computations. At the end, we have our picture. How is this done, like those computations on the GPU? Well, usually it goes along the logical graphics pipeline. So logical graphics pipeline, we have a model, then the vertices get inserted, then we do some vertex transformations with the vertex shader. So vertex shader is like where we insert our own piece of code. Then we do some transformations. If we want, we can also add tessellation, further transform the model. Then it goes to the rasterizer. The rasterizer determines what pixel gets affected by this model. Then the pixel shader is executed to compute the final color, and at the end we have our image. So you may have noticed that here in the logical graphics pipeline, there are no compute shaders, right? So what about them? Well, the thing is, compute shaders are not part of the graphics pipeline. They're like a separate concept. So but let's look again at the graphics pipeline. What's happening on the hardware if we submit the draw command? So if we invoke the graphics pipeline. So what's happening? We have our draw command. It gets submitted to the graphics card. First, always the command processor starts. The command processor is kind of like the brain of the GPU. It tells the GPU what to do next. So if we have a draw command, then the command processor sees, okay, it's a draw command, so it's part of the logical graphics pipeline. So it sends the work to the graphics processor. The graphics processor is the unit on the hardware where we can locate, for example, the input assembler. Then the graphics processor gives the vertices to the compute units, and the compute units are the units on the hardware who execute the shaders. So first they execute the vertex shaders, then the output goes to the rasterizer determines all the pixels, then it gets back to the compute units, which are now executing the pixel shaders, the output goes to the render backend, and we have our output. So what happens now if we have not a draw command, but the dispatch command? So dispatch command means we are invoking a compute shader. Well, first we still need to start with the command processor because we still need to tell the GPU what to do next, right? So the command processor sees the dispatch command, and now it knows, okay, it's a compute shader, so we can go directly to the compute units. And the compute units execute the compute shader, and that's it. So you see we have less hardware units invoked when we call compute shaders in comparison when we call a vertex shader. And what about input and output? Well, input and output for compute shaders is provided via constants and resources, and for output, obviously, writable resources. This concept you can also see when you create the pipelines. So when you create a compute pipeline, you just need the information for the shader stage. But if you create the graphics pipeline, you not only need to provide information about the different shaders, at least one, the vertex shader, but you can also have, of course, pixel shaders. So if you want tessellation, geometry shader, and so on, you also need to provide information about the input assembler, about the rasterizer, and so on. So what can we conclude from this short section? Well, if you invoke compute shaders, you have less hardware overhead than if you invoke other shader types, because it's not part of the graphics pipeline. You don't have these fixed functions as the rasterizer, and that's why you use less hardware units on the physical GPU. But let's look how get shaders actually executed on the GPU. And to understand this, we kind of need to know for what purpose GPUs were designed. And they were originally designed to solve highly parallel problems. So usually you have a lot of vertices, right? So one model can consist of millions of vertices. And all of these vertices may go through the same kind of transformations. The same holds for the pixels. All the pixels go to the same set of instructions because the final color is computed the same way. So you can say you have one shader for many pixels, one shader for many vertices. So it's a highly parallel task. And for vertex shaders, the smallest work unit is a vertex. For pixel shader, the smallest work item is a pixel. And for compute shaders, we call the smallest work item a thread. It's important here to note that you don't confuse it with the concept of threads on CPUs. Here, during this talk, if I say thread, I mean the smallest work item for compute shaders, just to keep that in mind. So how is this parallelism now realized on the hardware? Well, first we have SIMD units. SIMD stands for single instruction, multiple data. And then we have several SIMD units grouped on one compute unit, and we have several compute units. But let's look a bit closer on what compute units actually are and how they look like. And for this, we look at a concrete example, for the GCN architecture. Important is that the concepts I explain here, according to the GCN architecture, they translate also to other GPU architecture types. It's just easier to look at a concrete example, but the principal concepts, how it's designed, they're always the same for all types of GPUs, basically. So in case of GCN, the compute unit has 4 SIMD units, and each SIMD is 16 wide. And then also a bunch of widget cells, caches, and scheduler, and so on. And if you look at the whole GPU again, you see like there's a bunch of compute units. And just to give you a feeling for the numbers, for example, a Vega 64 has 64 compute units. And again, each compute unit has 4 SIMD units, each SIMD unit 16 wide. So this is this parallelism you see on the GPU, on the hardware. So now, how gets the work actually distributed on our SIMD units? How do we schedule the task? Well, we could, of course, schedule each single thread to the SIMD units, but that's not very efficient, right? And that's not how it's done. We actually have a hierarchy of work items. So if we call it dispatch command, we specify dispatch and then the parameters x, y, z dimension that determines the number of thread groups. So in this example, we have a dispatch call dispatch 432. And this means we invoke in total 24 thread groups. What are thread groups? Well, they're a group of threads. And the size of the thread group you can specify in the shader. So a dispatch call is on API side in your C++ code. And then the size of the thread group is in your shader code. So if you use HLSL, you use num threads, and then again x, y, z, and it determines how many threads are in a thread group. So in this example, num threads 824 means you have 64 threads within a single thread group. So this means in total we have 1,536 threads for this whole dispatch call. And then if you look, for example, at a specific thread, you can determine different kind of indices. So for example, this one has the ID, the thread ID within the thread group is 510. The ID of the thread group is 210. Then the ID of the thread within the whole dispatch call is 2130. And you also can access the ID of the thread within the thread group in 1D. So this would be 13. And those indices you can access in your shader code. So, but how does this hierarchy of work items now affect how the work gets scheduled on the GPU? Well, first, each thread group gets scheduled to a single compute unit. So, for example, thread group A gets scheduled to compute unit 0, thread group B gets scheduled to compute unit 1, and so on. And then, if you look at the thread group, the threads get scheduled to the SIMD units. How get the threads now scheduled to the SIMD units? They get scheduled to the SIMD units in bundles. Those bundles can have a different size according to the GPU you use. In case of GCN, it's 64, and we call it wavefront. Can vary. For example, in NVIDIA, it's usually size of 32, we call it warp. In GCN, it's now 64 in wavefront. The number itself is not that important. It's just important for you to know that there are like subgroups in which the threads get scheduled. And those subgroups is like the smallest scheduling unit. So we can't schedule anything less than a wavefront. And it's also important to know that we can schedule several wavefronts on one SIMD unit. Why is this? Well, just imagine we have one wavefront on our SIMD unit, and the instructions get executed, and then we have a memory load. Memory loads take a lot of time. So now we have two options. Either we just wait and do nothing and just wait until the data is finally there, or we instruct the memory load, and then while the one wavefront is waiting for the data to arrive, we continue with another wavefront. And this is to hide latency. That's why there's the concept that we have several wavefronts concurrently in one SIMD, just to hide this latency. So you may have noticed that in our example, the thread group has in total 64 threads. This basically means that this thread group has just one wavefront, and this also means that the whole thread group gets scheduled to one single SIMD unit. If the thread group would have, for example, 128 threads, this would mean that the whole thread group gets scheduled to two different SIMD units, because we have two wavefronts. And each wavefront gets scheduled to different SIMD units, usually like one robin, so first wavefront to SIMD unit 0, and the second wavefront to SIMD unit 1, and so on, depending on which SIMD unit has capacity for a new wavefront. So what can we conclude from this kind of scheduling? Well, first we know that the thread groups are usually on different compute units. So if thread groups need to communicate with each other, the communication needs to be cross compute units. And how can this be done? Well, the communication needs to go at least through the L2 cache, if not even to the global memory. And this takes quite a long time, right? So we kind of should keep it to a minimum that thread groups communicate to each other, because it takes a long time. But what about threads within a single thread group? Well, we know they're on the same compute unit. And on single compute unit, we have the L1 cache, for example. We also have registers, and we have the special memory called local data share. And we can use this local data share explicitly on compute units, compute shaders, to communicate with each other, so that threads within a single thread group can exchange data. What is local data share? Well, local data share is a special kind of memory, which is also used by other shader types. For example, the pixel shader used is for interpolants. So in case of pixel shader, it's already used by the hardware implicitly. So we as programmers, we can't access it explicitly. But that's not true for compute shaders. For compute shader, it's simply not used, so it's free to us. We can use it for whatever we want. And how can you access this in the shaders? You use the group shared storage modifier, and then you can just store your data there from one thread and read it from another one, for example. The only important part is here that you synchronize. So if one thread writes something to the local data share and another thread wants to read from it, you need to be sure that the data has been already written to it, obviously. And for that, you need to insert barriers. So what can we conclude from this section? Well, cross-thread communication takes a long time, because it needs to go at least through the L2 cache, so we need to keep it to a minimum. But for thread communication within a single thread group, we even have special memory we can use, the local data share. And this is quite fast. And maybe you have realized, what about threads within a single wavefront? Well, there are even special instructions called wavefront write instructions. I won't go too much into detail into this talk, because it would just exceed the scope. But I just want that you have heard about it, and you can look it up later. I will also have a small example later on this, but just you know. And wavefront write instructions, there you can even use the registers to exchange the data very fast, or just bypass kind of like in a special way the local data share, and that's like really efficient that threads exchange data with each other. Okay, so now let's get a bit more practical and see how to program actually. So, programming. Let's look at an example again. So, quite like easy example. So we have like the instructions float A equals index plus B, and then integer Z equals group index plus X. So index is the 1D index of the thread within the thread group. So it's per thread. And group index is the ID of the thread group. So what can we note here? Well, float A is different per thread because it's based on the thread ID, right? But integer C is the same for each thread of this wavefront because it's the ID of the thread group. And we know all the threads of the wavefront are from the same thread group, right? So we know it's the same value. This means for integer C, it's enough to store one copy because it's the same for all the wavefronts. But for float A, we need to store for each thread its own copy. So 64 copies, basically. And those, if it's 64 copies, we call it non-uniform variable. And of course, it requires more size because we have 64 copies. But if you just need one copy, then it's usually a uniform variable and it requires more size. And those uniform variables are stored in the scalar registers, and non-uniform variables, non-uniform variables are stored in the vector registers. Vector registers, we have in total more, like 64 kilobyte times 4. And for scalar registers, we only have 12.5. But since we need for one variable way more space, in case of the non-uniform variables, we can store in total less non-uniform variables than uniform variables, just because they're so way bigger and require more size. Why do I note this here? What's important about this? Well, the thing is, if we have used all our registers, we can't schedule another wavefront. So just imagine one wavefront uses 32 kilobyte of VGPRs. Then we have the second wavefront, which also uses 32 kilobyte of VGPRs, and so on. And then at a certain point, we can't schedule another wavefront because we just don't have enough registers anymore. We don't have registers left to store any intermediate state, and this means, okay, we just can't schedule another wavefront on the SIMD unit. So it reduces the maximum number of wavefronts we can have per SIMD. And this, in turn, reduces the ability to hide latency. So it's always preferable to kind of don't use too much VGPRs. So if you have like really complex and long shaders, they tend to use a lot of VGPRs. And like smaller one, obviously less. And also, if you can, it's not always easy to do that because you can't always really like decide if VGPRs or SGPRs are used. But if you have like the choice between using non-uniform or uniform variables, maybe you should tend to use uniform variables because they get stored in the SGPR registers, and of them you have quite a bunch, and you can't basically get limited on SGPR registers. So, but let's look at this one instruction a bit closer. So float A equals index plus B. And the one next to it is the translated ISA code. So just to understand it, that V in the beginning means it's a vector instruction because it's non-uniform. Then the add because it's an addition, and then F32 because it's the float, this is the data type. And then V2, V0, V1 are the vector registers with our data. So this basically V0 plus V1, and the result is stored in V2. So since it's a vector register, we have 64 copies per thread. But now imagine we have a wavefront, like we have a thread group with size total 4. So in the compute shader, there's the num threads 4, 1, 1. We still need to schedule a whole wavefront because we can't schedule anything less than a wavefront. So this means we still have those 64 threads. But since we only need 4, we deactivate 60 of them and just hold in the first 4 valid data. And this deactivation is done via the execution mask. So the execution mask indicates which threads are active and which one are inactive. In our example, the first 4 are active, and this means only in those copies of the variable is valid data, and in all the other ones, they are inactivated. So this means the data which is stored there, they're kind of like useless. They don't make any sense. It's invalid. And then, this instruction gets executed. But remember I said in the beginning the SIMD is 16 wide. Well, this basically means that the instruction gets executed 4 times. with each 16 threads. And even if all of those 16 threads are deactivated, it still needs to go through it. So this also means that it's preferable to have a thread group size which is a multiple of 64. Just because of this, because we need to schedule those instructions anyway. So you don't really save something if you have like less, like a smaller thread group size than 64, or like number which is not a multiple of 64. So the execution mask is also used for branches. So how do branches work? Well, let's look again at an example. So you have like if condition, and then if branch, and then else branch. And this is kind of like the ISA code related to it. We go through thread by step, and after that you will understand what each line of the ISA code actually does. So just from a conceptual point, we have like block A. In block A, we evaluate the condition and determine, okay, which thread needs to go into the B block. B block is the if clause, and which thread needs to go into the C block, which is the else clause, and then D is kind of like clean up and then just do whatever comes after the branch. So it starts with that we save the execution mask. So just imagine we have like our code, our threads are running, and then we hit the branching. And our execution mask at this point says that all threads are active. So this information we store. We just store, okay, all the execution mask says for each thread that's active, and we store it. Then we evaluate the condition, and the result of the condition test is stored in register S23. This evaluation of the condition itself doesn't modify the execution mask at all. The execution mask get modified in the next instruction when we move the result of the condition test over to the execution mask. Then all the threads which return true in the condition test are now active, and all the threads which returned false are now inactive. Then we check if we can go a short path. So we check if the execution mask is 0. This means that all the threads returned false, so we don't need to execute the if branch. Well, in this example, we need to go into the if branch because some threads return true, so we need to execute it. So it goes into block B, the if part gets computed, and with the respective execution mask, so some threads are activated, other threads are inactivated. After the if part is done, we invert the execution mask. Then we check again if we can cut make a short path, we can skip the else block. In this example, of course, we can't skip it because some threads returned false. This means they need to go into the else branch. Then the else part gets executed. And then after the else part, we restore the initial execution mask. So we reset kind of the execution mask on a state how it was before. We hit the branch. So in this case, we activate all the threads again, and then we just go on with whatever comes next. So what can we conclude from this way how branches are executed? Well, it means as soon as one thread falls into one block, the block needs to get executed for all threads, basically. And we only can skip a block if no thread of the wavefront falls into it. So this means we kind of want to avoid this diversion control flow. So we don't want to have this, that it goes from A into B and then into C and then into D. We kind of want to take one of the shortcuts so that it's either A, B, D or A, C, D. How can we enforce this? Well, first, we can enforce this if we use scalar comparisons, because scalar comparisons return for each thread, well, obviously the same result, because we just have one copy for the whole wavefront. Or we can, like in specific cases, you can also consider wavefront-wide instructions. And the specific wavefront-wide instructions are wave active any true or wave active all true. Wave active any true basically returns for all threads true as soon as one thread returns true. And wave active all true is kind of the opposite. It only returns true if all the threads return true. Otherwise, it returns false for all the threads. And this is also scalar because it's the same result for all the threads in the wavefronts. And in this way, you avoid divergent control flow, and you avoid the need to go into both blocks of the branch. So what can we conclude from this programming section? Well, first, you are limited on VGPRs. You can't store like an unlimited number of like intermediate values. And if you use too many VGPRs, you reduce the number of waveforms you can have on a SIMD, and this reduces the ability to hide latency. Then you should try to avoid divergent control flow, because it means you need to go through both blocks, the if and the else branch. And this is obviously not that efficient as if you can just skip one of them. And you can enforce that one block is skipped by using scalar comparisons, or in some cases you also can make use of the waveform-wise instruction. So, but now let's look at examples. Downsampling, the example itself is not that complicated, I would say. So it's basically just, we have a texture size. In this example, it's 4096 and 4096, and we want to downsample it down to 1. We want to store each intermediate level. So here, 4096 squared, then the first intermediate level is 2048 squared, and so on. We use the reduction factor from 2 times 2 down to 1 times 1, and we want to store each of the intermediate levels. So this basically means that we have a texture and we want to compute all the MIP levels of it. How can we do this? Well, of course we can solve this problem using a pixel shader. Usually how it's done is that you save each intermediate level as a render target. So we have the first pixel shader pass, where you have the texture size 2048 squared attached as a render target. You invoke your pixel shaders, they compute it, and then once this pass is done, you go to the next pass, which is computing the next intermediate texture, and so on. So this picture is a screenshot of RGP. RGP is a profiling tool you can use to see how much work is currently in flight on the GPU, how many threads are concurrently running, how many waveforms. And for example, in the 2048 pass, where this intermediate level gets executed, you see like a lot of waveforms are in flight, so the GPU is very busy in computing all those results, and so on. And then you see the next pass, 1048, again, we have a lot of work in flight. It's not that long anymore, because obviously the texture got already smaller, so we have less pixels to compute. And this holds for each new intermediate level. We have less and less work to do. And so you can observe here two things. The first is, after each intermediate levels, we have like gaps. Those gaps are caused by barriers, because before we can compute the next intermediate level, we need to be sure that the previous intermediate level is done, because the rest will depend on each other. So we can't compute the 1024 squared size level if we don't have the 2048 squared level already computed, because it's based on this. So we have to wait that the pass is completely done before we can start with this next pass. And then you also notice that when we compute the lower MIP levels, so MIP levels with size of just 1, 2, 4, like really small ones, there's not much happening on the GPU. We just have a few threads, they're computing a few pixels, and that's it. And the rest of the GPU is basically not doing anything. It's just idle and just waiting for the few threads to finish. And this does not really look efficient, right? So we basically have like an idle GPU just waiting for a few threads to the work, and we have a lot of barriers. The GPU is basically just waiting to be sure that they're really done, and yeah. So the question is, can we do better? Well, with pixel shaders, it's a bit difficult, because the pixels only can access the pixel in the render targets they're assigned to, so they can't access other pixels in this render target. So we kind of can't share the results across the pixel shader invocations. So this means we need really separate passes, because we can't share the intermediate results in one pass. But this is not true for compute shaders. In compute shaders, the output is provided via UIVs, so unordered access views, and there basically the entries of the UIVs, they're accessible by all threads. And so we can combine the computation of all the intermediate levels into one pass. So it's like a single pass solution. And if we program this and then take also a capture of RGP, it kind of looks like this. So what you can observe here, so we don't have the gaps anymore because we just have one pass. So we don't have that one pass needs to wait for the next pass because there is just one. And we also don't have like this long end where the GPU is not doing anything. It's got quite reduced. So now it's just like 10% of the whole work where there's not much happening in the lower ends. And in the pixel shader solution before, it was about like 1/3. And if you measure like the time, it's actually a performance gain of about 100%. So now you will ask, how is this done? How can we do this using compute shaders like for real? So the idea is that we have our initial texture, and each thread group we give a subtexture and let it operate independently on it. Because we want to avoid cross-thread group communication, right? Because it's really slow, it needs to go to L2 or global memory. That's why we want to give each thread group independent work. So each thread group gets a subpatch. In our example, we give each thread group a subpatch of size 64 squared. And those 64 squared subpatch get downsampled to 1. So this means that each thread group gets a subsquare of 64 squared. This is a subsquare of the source texture, it's 4096. Then the 64 subpatch get downsampled to 32, which in turn is a subsquare of the first intermediate level 2048, and so on, until the 64 subpatch got downsampled to 1, which is a pixel of the intermediate level 64 squared. And now we only need to compute the last MIPS. So the remaining 64 squared and down to 1. How is this done? Well, the last thread group we have is doing another round. How can we determine that the thread group is the last one? It needs to be the last one because we need to be sure that all the other threads are finished. So this intermediate level is completely computed. For that, we need to use a global atomic counter, and this actually is thread group communication. So we can't get away from it because we need to be sure that all the thread groups are done, so that we know, okay, this intermediate level is computed completely, and we can downsample it again. But this is okay because it's basically just a global atomic counter, so it's basically just one integer which just gets like increased. And then the last active thread group will know it's the last active thread group because according of the counter on its value, it knows, okay, I'm the last one, and I need to do another round of 64 down to 1. Also important is that this one intermediate level of size 64 squared is bound as coherent memory. This means that all the pixels are visible at least in L2 cache. Because if the thread groups like compute the intermediate level just by itself, it's enough if the intermediate level gets stored in L1, and they don't need to be visible to the other thread groups because they operate independent on it. But for this specific level, it's important that all the thread groups see the results of the other thread groups because they need to operate on it. That's why it needs to be bound as coherent. So, and this last part, where not much is happening, this is actually the last thread group which is doing another one of 64 down to 1. And you see, I mean, it's not ideal, but it's not that bad anymore. And it's because it's just a few pixels, it doesn't take too much time. So just to sum up, well, each thread group performs downsampling on its own subpatch independently from each other thread group. So a subpatch of size 64 times 64 down to 1. And then we have the last thread group which does another round of 64 down to 1. So the total number of thread groups we invoke obviously depend on the original texture size. So in our example, the original texture size was 4096 squared. This means that this original texture contains 4096 subpatches of size 64 squared. This means we have a dispatch call with 64 64 thread groups. So we have a total of 4,096 thread groups involved with this one dispatch call. And then, of course, we can have different configurations. So we can have different texture formats, 1 channel, 4 channel, 32 floats or 16-bit floats. We can have different reduction factors. So this one was 2 down to 1. And of course, the thread group size itself can vary. So we can have thread groups with 64 threads, or we can also have thread groups with 128 threads. And actually, I a bit lied to you before, because this RGB capture wasn't taken with a thread group of size 64 threads, but it was taken with a size of 256 threads. Why? Well, it just turned out in doing the testing that it uses the cache better. But really, the takeaway point here is that you always need to measure which configuration is the best for your specific problem case. So there's not one solution I can present. It really depends on different factors, on how much work you maybe have concurrently in flight, what's your texture format, and so on. So just measure what works best for you. And in this case, it kind of was 556 threads for one thread group. Okay, but computers can, of course, also be used for other stuff. So for example, you can call geometry on compute shaders. You can do particle simulations. You can do tiled lighting, terrain calculations, tessellation, and many, many post-processing effects. So basically, all the full screen effects can be just ported on compute shaders, because you don't really need the graphics pipeline. You just save, like, kind of use this work the vertex shader is doing by a full screen pass. You can just invoke a compute shader. Then you can also make async compute. Async compute means you can overlap compute shader work with graphics pipeline work. And what is a quite typical example where async compute works out quite well is overlapping SSAO with shadow map calculations. Because SSAO use different hardware units than the shadow map calculations. So we can really utilize the different hardware units on the GPU quite efficiently. On Vulkan, you can even present on the compute queue. So this gives like the nice opportunity that you move your whole post-processing part to the compute queue, present on the compute queue, and while the compute queue is calculating, computing all the post-processing efforts, you can already start the next frame on the graphics queue and do like your geometry work. So, yeah. So that's basically the last slide. Just to sum up, compute shaders offer nice properties. We have this hierarchy of work items. So we have concrete access to the thread groups and the threads. And with threads within a thread group, they can share data using LDS. You can even use waveform byte instructions to use registers. And yes, you can access the output from all threads, and you have less hardware overhead overall. Then it's also important that you keep some like programming guidelines in your mind to make sure that your computers are really efficient. This means cross-thread group communication should be kept to minimum because it's really slow. It goes to L2 or even global memory. This kind of diminishes the advantages you have by using compute shaders, so you should avoid this. Then also avoid divergent control flow. This also holds for other shader stages, and the same is for VGPRs, because then you hide the to reduce the ability to hide latency. Yeah, but that basically was it. Special thanks to those amazing people. Without them, this talk would not have been possible. And now I'm basically open for any question. You can ask now, you can send me an email, you can drop me a message or subscribe me after the talk if you don't want to ask here in public. And thank you a lot.
Thank you very much, Lynn. So, well, we have quite a lot of time, so you're welcome with your questions if there are any. Come on. Okay, yes, we do have a question.
Yes. So, yeah, thank you very much for this presentation. It was very interesting. But I noticed that I have lots of problems with understanding of the, certain or some definite hardware. So for each GPU, it's kind of different. And I noticed that with the compute shader, there's a problem becomes more clear, and with the Vulkan maybe it's more clear even. So is it possible to get this information somewhere or find something common between different GPUs or something like that?
Usually yes. For example, about the GCN architecture, you can look it up in the internet. There are also, for every new GPU, there are usually white papers published by AMD, NVIDIA, and there you find details about how the architecture is basically designed, and also some programming, like good practices and stuff. There are, by AMD and also by NVIDIA, there are a lot of like talks like this, where those facts are presented. So just look in the internet basically, and you will find it.
Okay, thank you for great presentation. So the question are, as for me, the compute shaders very similar to the OpenCL compute kernels. Yeah. So the main idea, what's the difference between the OpenCL kernels and the compute shaders, and where should be used compute shaders, and where maybe it's better to use OpenCL for computation or whatever? Thank you.
Well, I think it depends on your application. So this is mainly targeted for game programmers, right? And in game programmers, you do graphics work where it really makes sense to use the graphics pipeline, but at the same time, you also want to use compute shaders. And by using compute shaders, they're included in the same like ecosystem by using graphics, the graphics pipeline and compute shaders. By OpenCL, you only have compute shaders basically. So this is more like for your scientific examples where you don't need the graphics pipeline at all. So it really depends on the application.
Thank you. One more question.
First of all, thank you for your presentation, and I have a question. You said that compute shaders, they provide information to other shaders like pixel shaders and vertex shaders, but is there a way to retrieve information that the compute shader processed so we can use it in CPU applications and other things?
Yeah, you need to synchronize. So basically, you have your memory on the GPU. For example, your output resource is in GPU memory. And then you just need to load it to a CPU visible memory. So this is special like copy instruction that is visible from the CPU. And in case for AMD, there's actually special memory which is on the GPU but visible to the CPU. So the CPU can access this directly. But this depends on the memory type you're using. And then you just need to synchronize and transfer the data from device local memory to host memory if you want to access it from the CPU. Does this answer your question? Good.
Hi. Great presentation, by the way. But I had a question. So you said that compute shaders provide less overhead compared to the graphics pipeline, but if someone wants to produce their own graphics pipeline using the compute shaders and nothing at all from the original, what will be the overhead compared to the graphics pipeline, original graphics pipeline produced by the GPU vendors? And well, obviously there are many optimizations, but what are the difference between those in performance?
Well, the thing is, if you kind of want to simulate the graphics pipeline on the compute shaders, you need to be aware of that the graphics work, which is done using the graphics pipeline, they use very specialized hardware units on the GPU. So like very fixed functions and hardware units, they are just designed to do this work. And if you now use the compute shaders to do this kind of work, it's basically you use hardware units which are not designed for this kind of work. So I would recommend, if you really want to do like graphics stuff, to do it also on the graphics view, because there you use like the most specialized part of the hardware which are doing this.
Thank you.
Hello, first of all, thank you for your presentation, and I have a few questions to you. First of all, if there is a big difference between Direct 3D and Vulkan, if we talk about compute shaders. Second one, what is the most things in the shaders which are impacting the performance in general, and if there is any plans in advanced micro devices to implement raycasting in their graphics cards. Thank you.
Okay, so the first, now there are no big differences. Sometimes, like in Vulkan, you have different extensions than for DirectX 12, but the concepts in principle are the same. So they get translated to the same like intermediate language on the hardware. So it doesn't really matter if you use DirectX or Vulkan. Just if you want to, for example, use explicit Vulkan extension, but that's a very specific case. And in general, you could also just do it in DirectX 12. Then the second one, it's also hard to like give a general answer because it really depends on your problem case. I mean, like the general rules are avoid branching, don't use too many VGPRs and stuff like that. Like make sure that your code can really be executed as parallel as possible because that's what the GPU was designed for. And for the last question, I can't really give you a concrete answer. I just can say we are working on it, and yeah, let's see how fast we are. But we are working on it actively.
Thank you very much. Do we have more questions? No? Oh, yes, we do.
One more question. It's a bit about CMD instructions. We also have those instructions on the processor, and modern compilers for C++ do the optimizations like loop unrolling and stuff. Are there any chance that in some future the compilers will actually perform optimizations like moving the C++ code to the GPU?
Well, the fact is that the designs of GPUs and CPUs, they get closer and closer to each other. So nowadays, a CPU also has a lot of like many cores, like a Threadripper, for example, and it also gets more parallel. Of course, there's still differences, also in kind of the type of work you schedule on a CPU or on a GPU, but yeah, it's fact that they get closer and closer to each other. And I'm not sure about C++ on the GPU. I know there are some like hobby projects where they like invent new shader languages which are very similar to C++. Also heard like from a student project where they wrote a compiler for C++ code, which compiled C++ code to SPIR-V code, basically. And this would kind of like be actually what you suggested. So there are movements in the community to do this.
Okay, thank you.
Thank you very much, Lou. Thank you for your questions.
Yeah.
Thank you.
Thanks, yourself.